Hello and welcome to another creative coding video. Today we're going to take another look at using math functions to create interesting designs. This is the third video on this theme. The first video was quite long and covered quite a lot. The last video was much shorter and really looked at using the wavy sine function to create interesting designs. Today we're going to be looking at another math function which is quite a popular one because of its unique shape, and this video again will keep it short and simple so we can really get into understanding how it works and how we can use this math function. So super quick reminder, math functions have shapes like y equals x. We saw it's a straight line, and we saw y is x squared has a curvy shape, and the interesting one we saw last time was a sine function which goes up and down, and we used the shape of that to decide where to draw circles and rectangles. Today I'm going to be looking at another function which goes by several names. The most friendly name I guess is called the bell curve. Some people call it an exponential decay. It's a variant of that. Let's look at it. Let's not worry about the words. Let's just look at what the shape is. So an exponential function goes up like that, exploding exponentially or growing exponentially. That's where the phrase comes from. If I square that x, it gets big even quicker. But if I do a negative there, it creates this sort of upside down bowl or a bell kind of shape. Let's zoom into that a little bit so we can take a closer look. And it's a nice one because it has a very smooth characteristic. It starts falling slowly, speeds up, but then slows down again, and it never quite reaches zero. And those are some interesting properties which can be useful for us. But for us, this decay, this smooth decay, is what we're going to take advantage of. This nice rolling off. So let's go to our code. Now I'm logged in as usual into Open Processing. Got my simple library enabled, and I've got simple set up over there. And I've written a repeat instruction, simpler than the one we did last time. There's no loop counters. All it's saying is, this function blob, call it 500 times. So whatever blob is doing, do it 500 times. That's the 500 there. And this is the blob function here. And it's empty at the moment because I haven't written anything in there. So let's make a start. So what I'm going to start with is drawing circles, small ones, just randomly on the canvas. We've done this lots of times before, so it's nothing new. Hopefully, we're going to pick a x location, which is a random number between 0 and 800. That's the size of the canvas, and y coordinate, a vertical location, which is from 0 to 600. So those x and y should be somewhere on the canvas. Let's see that canvas. Yep, so it's 800 across and 600 down. So those positions should be somewhere on the canvas, but not outside like that. Cool, let's get rid of those dots. Now if I draw a circle there at that position, x, y, and draw a moderately small circle, I should get 500 circles randomly placed on the canvas. There you go. So that's our starting point. Nothing overly interesting there. We've done this lots of times. Okay, now let's change something. Let's say the size of those circles, they're quite small at the moment, aren't they? let's say the size of the circles depends on how far they are from the middle of the canvas. So let's get back to our little drawing pad. So middle of the canvas is here at 400, 300. And if I place a circle at random, let's say here, this distance is what I'm interested in. That distance. So if this is the center of the canvas and this circle is at XY, that distance, we could calculate it like we did at school using Pythagoras' theorem, but luckily our programming language makes it easy for us. It gives us an instruction called dist for distance, and we just put in the 2 points. So 400, 300 is this point, and then we say the other point XY, which is that one there, and that will give us that distance. Cool. So if this was close, that distance would be, like if it was here, that distance would be quite small, and if it was far away, that distance would be larger. So let's calculate that distance. So var d equals dist from x, it doesn't matter which order we do it in, 400, 300, xy. What I was going to say is, if you did x comma y 400, 300, it wouldn't make a difference, because the distance from one to the other is the same as the distance from the other to the first one. Cool, so we've got the distance. Now the distance is going to vary probably, well, let's have a look at the canvas. The largest distance might be around 1, 2, 3, 4, maybe 500-ish from there to there. I'm guessing roughly. It's not going to be 2, it's not going to be 2000. You know, if from here to here is 1, 2, 3, 400, and this is 300, oh, actually that's 500, isn't it? By Pythagoras, if you remember that. Right, so just getting a rough sense of scale, that distance could go up to around 500. Right, so if we use that to draw, if we use that distance to be the size of the circle, that's going to get quite big, isn't it? So let's, because it could be a circle of size 500, and that would swamp the canvas. So let's calculate a smaller size. Let's say var size equals distance divided by, I don't know, let's say 100, and use that as the size of the circle. So that should mean that nearer the center of the canvas, that distance is small, so the size of the circle is small, so we have small circles. And as we move away from the center of the canvas, further away, the distance is large, and the circle size will be large as well. Let's see. They're still, well, they are smaller in the center. They are bigger over here. But maybe I made them too small. Maybe I should divide it by 50, say. That's a bit clearer, isn't it? Yeah. Let's say divided by 10. Yeah, that's kind of a, let's say divided by 20. If I don't draw so many, yeah, we can see that now. We can see that near the center of the canvas, the circles are small, tiny, and as we move away in any direction, the circles get bigger. So that's kind of nice, isn't it? So that's just showing that we can use something like a distance to calculate the size of a circle, to say this circle size depends on that distance. But we haven't used our bell curve yet. So let's try a different idea. Let me clear up this writing. Off it goes. Plop, 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 plop. Off you go. Right, so right now we said the size of a circle is bigger the further away it is. So as the distance gets bigger, the circles get bigger. Let's do something else. Let's say they're big near the start and smaller further away. So what do we know? What mathematical function do we know that can do that? Well, we've just seen the bell curve, which starts off at 1 and goes towards 0 as x increases. So we can use that. We say as the distance increases, the size gets smaller. So in effect we're saying d for distance, size, and it's going to start large and get smaller in a smooth roll off. So that shouldn't be too much extra code, might even be less. So we still need the distance, yet we're calculating the distance, and now we're saying the size is that exponential function. How do we calculate it? Minus x squared and then the exponential. So let's say math dot x, that's the exponential function, and inside we put not x but x squared, and not even that, we put minus x squared. So we said minus something squared, that's a square, and it was the distance. Now we might need to do some scaling here. Let's see what this does anyway. It's good to learn from deliberate mistakes. Well, they're all tiny, and the reason for that is this goes, the bell curve there goes from 0, where is it? There it is. Let's zoom out a little bit. It goes from 1 all the way down to 0. So the size of circles at the moment will be going from 1 to 0. That's why they're so teeny tiny. So let's multiply those by, say, 50, which means they'll go from, let's actually demonstrate that here, this scaling thing that we do. So we'll say the same, I'll just copy that and I'll put it there, but I'll say 50 times, and you can see the effect it has. Quite big there. Let's make it 10 times and zoom in there. Can you see, by multiplying it by 10, instead of going from 0 to 1, it's stretched upwards 0 to 10. That's how we make the shape of a function taller. We can make it shorter as well. Right, so we're multiplying it by 50. Let's see what effect that has. Something's still not quite right. And the reason is this d, the distance, goes up really rather quickly. See here, when it's about 2 and 3, it's already quite small. And if our distance is shooting off to 500, we can have tiny values, tiny circles. You see, by the time it's 2, 3, the distance is 2 and 3, it's already quite tiny. So we need to slow that down a bit. So maybe if we say divided by, I don't know, 100. Let's see if that has any effect. Yeah, that's a start. That is a start. So we've got larger circles in the middle that are closer to size 50, and as we move out, they get smaller and smaller. Let's add more circles back in so we can see the effect better. There you go. Yeah, it's nice, isn't it? And we can tune that a little bit. We can sort of say, I don't know, let me have a think. Let me slow that down even further so they're larger for longer. Yeah, you see? So by dividing that distance by 200, I've stretched that out even further. And now the circles are larger for a much larger area of the canvas. That's starting to look like some kind of virus or protein or molecule. Looks a little bit alien to me. So we could leave it there. This is an interesting design. Let's add some colour. Let's play around with colour. So let's use I don't know, let's use those red, green, blue, the red, green, blue mixing to make our colour. So let's say we fill it with something that depends on that distance as well. And we know size has been scaled down a bit. So let's say let me think. Let's say we say size 0, size. Let's see what effect that has. Well, let's have a think what effect it has. Near the centre of the canvas, size will be small, 0, right at the centre. So these should be black, and as we move away, they should get lighter. Yep, so it's definitely dark in the middle. No, I'm wrong. I got that the wrong way around. Near the centre, size is larger, and as we move away, size gets smaller, and those are the red, green, blue values get smaller. Got that the wrong way around, didn't I? Let's that was a bit dark, so let's up the colours a bit. See if I make them red, green 128, that is not that interesting. Let me take this one from 255. So 255 is the maximum it could be. So I'm taking size from 255. Just an experiment. There's not a lot of thought behind that. Let's see what happens. Okay, that's kind of interesting. Let's see what happens if I change the outline stroke. So stroke. Let's see. Maybe I'll do something similar, but just vary things a little bit there. See what effect that has. Again, I'm just experimenting there. Oh, that's kind of nice, isn't it? Yeah. That's got a nice kind of a high-tech glowy feel to it. Why don't I change the rate at which that goes up? So if I multiply that divide that by 2, again just experimenting to see if it makes it. I'm trying to get the colours to change more. Maybe I should increase that. There, now that's much better, isn't it? Yeah, I like that. Maybe I should try that trick up here. So I've multiplied the size. Okay, so that's got a lighter in the middle. I'd kind of like it to be... No, that's fine. Yeah, I like that. No, that's okay. You could just keep experimenting, couldn't you? Can't resist, can I? Yeah, that's nice. I'll leave it there. I'll leave that one there. No, I won't. Let me see what happens if I have 1,000 blobs. Will that be too much? No, that's not. That's still interesting. Yeah, maybe it's a bit too much. Maybe I'll go for 600. Yeah, I like that. That's it. Yeah, we'll stick with that. So that's really rather nice. So yes, I've spent a few minutes messing around with the colours and using the distance to work out a colour, but the main idea was we're using our bell curve here to make the circles start off large and then roll off in size and get smaller and smaller. Now they never get to 0, they get pretty small, but it's a nice way of having a smooth change that's easier on the eye. So whenever you need something that gradually falls off, that bell curve's a really good candidate. And as you've seen, the code is just that. This is for making sure that the x, or the value that goes into the function, is scaled right, and this defines how tall it is. Otherwise the magic just happens here. Nice and easy. I mean, we didn't even have to have all this stuff around, picking colours. So that's rather nice. I hope that's been interesting, useful. And this is the second example of using a maths function that we've looked into with more detail. Okay, I hope you have a go yourselves. Have an experiment, have a play. It's the best way to learn. And I'll see you next time. Bye.